Well, those were pretty good bagels. I had a good lunch.
Yeah, that was really good. Oh, pink bagels and blue bagels.
Wait, oh yeah, I wonder who put it here.
I don't know.
Yeah. Oh well.
Well, let's describe it. So, electric field, rotation.
Rotation of E field creates a time-varying H field.
Or if we had H there, it would create E. But now we're going to say E exists, creates a rotation H. But rotation H
creates an E field.
Creates an E. Rotating E creates an H. So what we have are two rotations that are cross-connected or coupled. And we can write it like this. 1/2 the curl of E is a rotation of E. It's a vector. And that's equal to, multiply that equation by 1/2, minus 1/2 mu dH dt.
Okay.
And then we can look at the same, multiply this equation by 1/2, rotation of H is equal to 1/2 epsilon di E di T.
Oh wow. What's with the 1/2 business?
Oh, the 1/2 business comes from a class exercise relating to the curl of velocity. And we'll actually show in the class exercise that 1/2 the curl of the velocity is equal to the angular velocity.
Okay.
And so that's a class exercise that really emphasizes the idea that rotation is done by the the grad cross operator, which we call the curl. So that's the important thing. So we have rotations that are connected, as we can see from the donut picture. So we're going to explore the implications of that shortly.
Oh, same board.
Same board. Oh, we're still here, of course. We just took a little break. Let's see. So we have rotation of E appearing here. But we also have E appearing here. And we have rotation of H here, appearing there. So this diagram illustrates the coupling of the rotation. So the last two Maxwell's equations are, you can see from the picture here, coupled rotations. Now, how do we uncouple the rotations? So let's uncouple. So this rotation of E is proportional to H. And this rotation of H is proportional to E.
So you want to find out equations that don't depend on each other?
Yeah, so we want to find an equation involving only E. So we need to do a little bit of cross-product fiddling here.
Okay.
So let's look at this. If I have E, like this, rotating around, then when I take the curl, I get a vector that way. And that vector is related to H. It starts to close on itself. I haven't shown that. Now, if I take the curl of the resulting curl, so I take E, take the curl, get this vector, take the curl again, where will that vector lie?
Back to the E plane.
Yeah, so if I take the curl a second time, I'll get a vector that lies in the E plane here. So you can think of the vector getting rotated and scaled. It's lying back in the E plane. That means if I take the curl of this equation, I'm back in the E plane.
So the curl of E.
The curl of E puts me back with E.
Wow.
If I take the curl of this,
then you're taking the curl of that.
I'm taking the curl of H, and we'll explore that in more math detail later, but the curl of H we can substitute for E from E here, so we get E on both sides, and that's going to give us a wave equation, as we'll see, that only depends on E. So, in summary, taking curl of E puts us back in the E, if you like, the E plane, the E rotation plane. puts us in the E plane,
Then does it mean by doing the curl of E, we could get the wave equations?
then we're going to get a wave equation in E.
And
Now-
you can do the same with H.
Could do the same with H. And later on in the course, we'll see that if we combine the ideas here with the cross-coupled rotations in the original four Maxwell's equations, we can then get an idea of how other devices behave, like waveguides, which we'll explore later.
Wow, thank you very much.
Good job.